Good day. This is 22 November. I am Professor Timothy Kentop. We're conducting an item analysis of the initial attempt of Module 5 assessment in CSC 241, Computer Architecture. Getting ahead of myself. 243 is next semester. There were 18 questions. The average student consumed 44 minutes out of a 60-minute period to engage each of those. The average score was a 3.75, which is about a 75 average overall. That's a good mix. There were a number of challenges. We'll review this quickly. However, the Blackboard algorithms calculated that there were 6 easy questions, 1 hard question, but most questions were considered to be medium in difficulty. That's a pretty decent mix. We don't have too many easy or too many hard. That's the goal. We want to run down the column here until we reach a point where it looks like everyone has items correct. The von Neumann diagram, where we filled in the blanks, appears to be the one that most everyone answered correctly. We'll go ahead through here to take care of the multiple answer questions, but we will not cover the multiple choice questions that were nearly flawless. 0.23 out of a 0.25 possible score for the class as a whole. We'll run down through this multiple choice here. There were a few students that had issues through this question here. Identify this component. First item that posed a challenge for most students in our Module 5 assessment was a true-false question that reads, according to computer hardware experts, it is always less expensive to build your own, a do-it-yourself approach. This is because you always save on labor used to assemble the components. That is false. The fact is, it all depends on market interests. So that doesn't always prove to be the case. The next item that proved a challenge for students is a multiple choice item that reads, when a computer system is turned on and power is applied, the same sequence of tasks are performed. Select the option below that best reflects the correct order of tasks. It is this answer that reads BIOS firmware loaded. That's what happens first. Then the power on self-test executes. So it runs through a series of self-checks on digital components. And the last thing that happens is that the boot disk loads into RAM. So that is the correct answer. A number of students picked this one where it said the power on self-test was first performed and then the BIOS is loaded. But the power on self-test basically executes from code that is stored in the BIOS. So the post doesn't have a chance to actually execute unless the code embedded in the BIOS is loaded first. I hope that helps with this answer. A third item posed a challenge for most students. It reads, within an ALU, a PC is that's arithmetic logic unit. A PC is and this always catches some students because they think, okay, it's a personal computer. No, it's called a program counter, a special register that increments to the next instruction unless a go to or jump occurred. It's called a program counter or procedure counter. Program counter, yeah. There we go. It's a special register within the ALU. So if you think about it, the ALU is a component of the CPU, which is a component that's installed in the socket of a motherboard, which is inside a personal computer. So the key to understanding this is within an ALU. The next item that posed challenges for many students was a multiple choice item that reads, upgrade Slowdown. It may be counterintuitive, but when you add a dual inline memory module, a RAM module, to improve your system performance, if it's not the same size and the same speed, it can actually slow things down instead. The question reads, buying a single larger DIMM or SODIMM. SODIMMs are small form factor memory modules that are installed in laptops and portable devices. Often slows a system down rather than speed it up, because a different size or speed means interleaving cannot be used. Now this is a huge thing. You always want to match the size and the speed of memory modules so that your computer can use those memory modules in tandem. When they're used in tandem, the performance is much higher. If you put a larger memory module in, you will have more memory, but they're not the same size, not likely the same speed. It'll always run at the speed of the lowest memory module, even if you have faster RAM in there. That's sort of a waste when you think about it. The next item that posed a challenge for students reads, it's about data storage criteria trends. With regard to data storage methods and technology, the further distance one travels away from the CPU, a noticeable trend for selected criteria becomes quite obvious. By trend, we mean that something becomes greater or less as distance from the CPU increases. Select the statement below that best reflects this trend. That has to do with the large table that's arranged in landscape mode toward the end of the study guide for Module 5. So what increases the capacity or size and volume of the memory increases, the volatility of the memory decreases. So the further away from the CPU you get, the more persistent the memory tends to be. The faster, more expensive memory modules like SRAM chips for level 1 cache and so on, the memory that's stored in there is extremely volatile, meaning it's non-persistent. It doesn't last. That's the issue. Down here, latency and persistence. That first component, latency, increases. It doesn't decrease. Latency means delay. So it gets slower as you move down the page or down the table. Latency actually increases, meaning the delay increases at a greater distance. I hope that helps. The next question that posed a challenge for many students reads, it's about 12th generation Intel CPUs. You are to perform a simple task where you promptly identify which among current and previous Intel CPUs are 12th generation multi-core fabrications. The only reference you were allowed is a quick view of an image showing the primary CPU components present. Which attribute on the die will confirm the processor is a 12th generation multi-core chip? Well, beginning with the 12th generation, Intel and some other chip manufacturers decided to differentiate between core types. Instead of having identical CPU cores, they created certain cores to perform efficiency operations, just the kind of routine stuff that an operating system does, input, output, memory swaps, that kind of thing. The other cores are called performance cores. So what's obvious is that the cores, you have a set of smaller and a set of larger cores. That's a distinct difference When you look at 11th generation and earlier, or older, 11th generation and older CPUs from Intel, they're all the same size and shape, and they're identical cores, and they're all performance cores. So, what is virtual memory? This question posed a challenge for some students. An important innovation, virtual memory, greatly improves hardware limitations common to all personal computers. Choose the statement below that best describes what virtual memory is or does. Virtual memory utilizes faster disk space and works like artificial RAM. That's the simplest explanation. Some students answered utilizes faster RAM segments or pages to enhance hard disk access. That's not accurate because RAM segments don't differ in their speed. Although logical, so there's a convention in operating systems we go into in memory management called logical pages, which is different than physical memory frames. Hardware layer kind of thing. We'll leave that for the 410 class. In any case, just remember that faster disk space is reserved so that temporary RAM data can be stored on the faster disk space. That's what virtual memory is. It is artificial RAM. It's simulated RAM by using the fastest disk sectors. Remember that traditional disks spin, so some of that starts to change when you start using solid state drives. We'll continue through these 3 multiple choice items, and then we'll continue on through the multi-answer items. The fuss about GPUs. It was recently discovered that the design of dedicated video graphics cards, popular among computer gaming enthusiasts, were ideal for use to build a platform for supercomputing. Select the attribute or feature that allowed these hardware resources to be used for such high performance computing, HPC, at such a low cost. Well, graphics cards contain a processor that has many smaller floating point calculation cores. They're called CUDA cores, adapted for floating point calculations. That's because the floating point calculations that are so common to gaming environments have to do with graphics, and it's mostly vector calculations in order to get realistic video graphics simulations and realistic physics responses that look like real-world physics. A lot of that has to do with floating point calculations. Floating point calculations involve decimal points. And the other thing you can do with gaming cards is you can connect 2 or more of them together, and they have dual port video memory, so you can read to and write from the graphics memory at twice the rate that you can with regular system memory. So that's very high performance stuff, and given the amount of money that you'd spend for a graphics card, it's a lot less than a supercomputer. The flow of memory. The flow of memory stored. So when we look at virtual memory, one thing that becomes very obvious is that there's a distinct difference in the way that some memory is stored and retrieved. The important thing to understand here is that when it comes to the physical layer, when you're dealing with RAM or physical memory modules, especially SRAM, static RAM, there's a first in, first out kind of process that ensues. So if this red arrow represents data, basically it doesn't stay long on that chip. It's first in and first out. That's called FIFO. However, virtual layers of memory first in, last out, right? It runs on top of the hardware. It's not below the software on the hardware. It runs on top of the software. And the way this memory flows, first in, last out, that's an important thing to understand about virtual memory and how it's distinctly different. It's also worth mentioning when you move on to CSC 243 and we begin to talk about network performance and the flow of data in networks, you see an awful lot of specialized network equipment like switches and routers that make use of the FIFO data flow algorithm, right? So there's a lot of information that is basically turned around very fast, first in, first out. So that's just something important to remember. When you store to a hard disk, you got to take a longer route, and first in, last out. Front side bus, this will be the last of the multiple choice and true false questions that we review. The question reads, the front side bus, or FSB, is a part of which component of a modern system board? Well, the data bus itself on the motherboard is that part of the motherboard that looks like a superhighway overlaid on top of landscape. There's when a lot of those data paths, parallel data paths, converge, it's said that they form up a bridge on the data bus. The north bridge is that part of the front, it's the front side of the bus. So the north bridge component is the front side of the bus where the highest performance components on a motherboard are located. The CPU, the RAM, the graphics cards, and high performance hard disk controllers. High performance network cards are also part of this, or fiber. The south bridge involves input, output, and other peripherals, printers, displays, keyboard and mouse, that kind of thing, standard hard disks, and so on. I hope that explanation is helpful. Now we'll take a look at the multi-answer items further down below this point. So these multiple choice questions were answered nearly flawlessly along with this true false multiple choice, this multi-answer, and the last multi-answer. So we have a diagram here that shows some detail, and in particular it shows the memory range for addresses in memory modules that are used to represent a virtual representation of a hardware component. That's what we're looking at right here. We showed you in class that if you go into Device Manager in the Computer Management Management module, that basically you can open up the Device Manager, and if you select properties for a given device, in this case the gigabit network card, you can select the Resources tab, and this is where the virtual network card lives in memory. It says, please view the diagram below and select each statement below that is accurate. This diagram shows how hardware is represented as a universal virtual resource. The operating system is often referred to as the virtual machine because it's built of generalized and virtual hardware components. The software applications are capable of accessing those resources even though there are different brands, different models, different components in every computer because of this magic here. And here it shows how memory address ranges are reserved for device access. So this is one factor of system memory use. Some of your system memory is actually used to simulate virtual components which are representations of the actual physical components. Every operating system does this. So it's really amazing stuff. We go into that quite a bit more detail in CSC 410, Principles of Operating Systems, and we touch on it in our Deployment Operating Systems class, CSC 255, for the tech certificate. Our last item is a multiple answer item. I don't think, yeah, the von Neumann was fine. Our last multiple answer item reads, CPU design is changing across the industry right now, and as a result, the basic model for a CPU provided by John von Neumann is no longer that simple. I mean, it's still the same basic plan, but it's getting very complicated. Select each innovation that is currently a CPU design trend. Well, many CPUs are no longer complex instruction set chips. Instead, they're reduced instruction set design. Okay? That's one trend that's going on. So instead of being general purpose, they're more specialized, especially where mobile devices are concerned. System components are now included on the chip, on the die itself. So you'll find wireless components, you'll find graphics controllers, you'll find all sorts of other digital devices that you would otherwise find on the motherboard. This is called System on the Chip, SoC, System on a Chip. So when the system components are built into the die of the chip, that's called System on a Chip. Another trend is that there's a class of chips that allow for adaption. The logic gates can be altered or changed after installation. These are called Field Programmable Gate Arrays, FPGAs. Hugely important. Now 3D XPoint and Optane that works like RAM and disk memory, that is an innovation, but it doesn't have to do with a computer processor. It has to do with disk memory. So that's why all of these are chip-oriented questions. This has to do with the motherboard data bus. Again, doesn't have to do with the CPU. Thank you for joining us with this item analysis of our initial version of the Module 5 assessment. We'll post the final version of the Module 5 assessment that you can retake as you prepare for finals week after Thanksgiving. We'll sign off for now, and thanks for joining us.